In this video, we'll talk about a special class of system that can be uh, that can be used to explicitly describe the behavior of a system, okay, which can be described by such linear, constant, coefficient, differential equations. Okay, so if it is a discrete time system, then such systems can be defined by a linear constant coefficient difference equation. Okay, so let's keep in mind that we are talking of causal LTI systems. Okay, and they are being described by differential if it is a continuous time system, or difference equation if it is a discrete time system. Okay, so an extremely important class of continuous time systems is that for which the input and output are related through linear constant coefficient differential equations. And equations of this type, they arise in the description of wide variety of systems and in physical phenomena. So, for example, if you are modeling the behavior of a or a response of electrical circuit consisting of RC components, you have a differential equation that relates the input signal to the output signal. Okay. Similarly, if you are defining mechanics of a moving vehicle in terms of the input, that is the acceleration, or in terms of the damping forces, frictional forces, you end up in a differential equation describing the input and the outputs, or you are modeling the kinetics of a certain chemical reaction. Okay, so many physical phenomena as such can be described, the behavior, that how system is interacting with the input to produce an output, can be described in terms of differential equations. Okay, so for and similarly, the same analogy applies to the discrete time systems, which can be defined in terms of linear constant coefficient difference equations. Okay, so equations of this type are used to describe the sequential behavior of many processes. The difference equations are also arise quite frequently in the specification of discrete time system designed to perform particular operations on the input signal. So, for example, now if you recall, in chapter 1 we talk of an accumulator system. Okay, so for a certain discrete time system, you see if what it does is to the input, it sums up all the samples. Okay, if it is summing up all the samples, this is an accumulator system. So, for example, it is summing up all the samples from, let's say, minus infinity to the present time index n. That means if you expand the summation start from minus infinity, then it ends up until n minus 1 up to the present time index n. Okay, so it's just accumulating the samples in the accumulator, right? And if you expand this, this can also be written as a difference equation, that is up until n minus 1 you can accumulate the past output up until n minus 1 and add to it the present sample x of n, and that's an equivalent description of the same accumulator system, and this is your first order, call it first order difference equation. So the difference between y of n minus yn minus 1 is your input. So basically the system is just summing up the samples over here. So this is showing the accumulated accumulation of all the samples up until the discrete time instant n minus 1, and then comes the present samples and you add it up to produce the output. Okay, so this is a difference equation describing the input output of an accumulator, right? Similarly, for example, the system that calculates the difference between successive input samples values, while another discrete time system computes the average value of the input over an interval, are described by difference equation. So, for example, for the first case, if you're computing the difference between the successive samples, that is, you need a difference to compute an output. So y of n is equal to x of n minus xn minus 1. You might be doing some smoothing operations. Okay, so you can filter out high frequency components. You might want a difference between successive samples. So this difference equation relates how the system is computing the output at the present time instant n. Okay, so these difference and differential equations are implicitly describing the behavior of the system, but explicitly how the input is related to the output. Okay, how you would define yt in terms of xt or y of n in terms of x of n? Well, then you have to solve for the difference equation. We are going to look at how these equations can be solved in a classical manner. Okay, so let's start with a linear constant coefficient differential equation. The first order constant coefficient linear constant coefficient differential equation can be written as such. Okay, so to introduce some of the now important ideas concerning the system specified by linear constant coefficient differential equations, let us consider a first order differential equation. Why it's a first order? Because it involves the first order derivative of the output. Okay, So I'll say, let's say n is 1, okay, the order is 1, which means we are talking of the first order derivative only. So where yt denotes the output of the system and xt is the input, okay. So very important point about the differential equation is that they provide an implicit specification of the system, as I've said before. So that is that they describe a relationship between the input and the output, rather explicit expression of the system as an output, as a function of input. So we don't know exactly how the output is related to the input. Okay, it could be some exponential function of the input, it could be a ramp function of the input, step function of the input. So we don't know what this function is. In order to evaluate this function explicitly, we need to find a solution to these differential equations, and in order to find an explicit expression, we must solve this differential equation, and to find a solution we need more information than that provided by the differential equation itself. Well, the more information will be once you evaluate this differential equation. You will need some supplementary additional information, or call it auxiliary information, because there will be some constants turning up that needs to be evaluated in the context of the behavior of system. Okay, so we need some initial conditions or constraints. So to solve the differential equation, we must specify one or more auxiliary conditions, and once these are specified, we can then in principle obtain the explicit expression for the output in terms of the input. In other words, a differential equation describes a constraint between the input and the output of the system. But to characterize the system completely, we must also specify the auxiliary condition. You see, if the auxiliary conditions are different, then they will lead to different solutions, right? So defining the auxiliary condition is very important to look at the behavior of the system, look at the some information about the qualifications associated with the system. For example, if the system is linear time invariant and it is also causal, then that means the output y of t will be same as the input, okay, up to a certain time, call it t naught. Okay, so what I mean to say is that up to a certain point, t equal to t naught, xt, okay, xt is your input, okay, and its behavior, however, the input is being defined. There is certain input behavior. Okay, it could be exponential, it could be rest. I mean, there could be no input up to certain input, up to certain instant in time t naught, right? So up to certain instant in time t naught, the nature of excitation, if it is at rest, let's assume xt is 0, then the output will also be 0, right? For 0 input leads to 0 output is a characteristic of a linear system. So let's say if for such a situation, for initial rest conditions, if your system is initially at rest up until a certain time instant t naught, then the output should also be 0 up until t less than or equal to t naught. Okay, that means system cannot anticipate the future. So unless there is a non-zero excitation on an input applied after t naught, the system gives an output. Okay, before that, system cannot anticipate what is going to be applied before t naught, right? So that implies causality. So we can derive some auxiliary conditions from the causal nature of the systems like that. So we can to ease the solution of to make this solution of difference and differential equations easier, we can assume that the system is causal. Okay, so it is non-anticipatory. So let's take some examples before that. So different choices of these auxiliary conditions lead to different relationships between the input and output. But we will focus on the use of differential equations to describe LTI causal systems. And for such system, auxiliary conditions take a particular simpler form, right? Okay, so let's take an example and let's show how these auxiliary conditions can be used and how we can solve the differential equation in a classical manner. So let's consider the following, again the same differential equation that we have talked that we've seen over here. So this is the first order differential equation relating yt to xt, and we don't know actually how basically this is defining the dynamic behavior of the system, but we don't know how the output is explicitly defined in terms of the input. Okay, it could be an exponential, we don't know, it could be a unit step function, whatever it is, this function we don't know. So let's see how we can solve this to find this expression of yt in terms of xt. So as an example, the input is an exponential and that is applied at for this UT is emphasizing that this xt is applied after t equal to 0, so it exists at t greater than 0, t greater than equal to 0. It's an exponential excitation to the system, and for this excitation we'll solve the differential equations. Okay, k is a real number over here, k is a real number, it's not a complex number. So the complete solution to the differential equation will consist of the sum of a particular solution. Okay, let's call this ypt. Okay, this is not double dot, so we'll call this as ypt, and a homogeneous solution yht. So the complete solution can be bifurcated into two parts. There is homogeneous solution to it, and then there's a particular solution to it. To the particular solution is of the same form as the input. Okay, as the input, this is xt, and the homogeneous solution h of t is the solution of the homogeneous differential equation. So the homogeneous solution is the solution to the differential equation when the input is 0. Okay, so this is also called the natural response of the system. Okay, over here it just simply implies that xt is 0. The forcing function is 0, so that is no excitation is implied to the system, and we're just evaluating the natural response of the system without any excitation. So common method for finding the particular solution for an exponential signal is to look for a forced response and the signal of the same form as the input. So you see, for a homogeneous solution, we solve the homogeneous equation, that is the input is made 0 first, and then y of t is solved for that. And in the second case, a forcing function is applied in the differential equation, which has the same form as that of the excitation. Ypt will be of the same form. So ypt over here in this case will be of the exponential nature. So since xt is of the exponential nature, we hypothesize a solution for t greater than 0 of the form ypt is equal to y, capital Y E3t. Again, y is some real number. Okay, and if you are going to substitute this in the differential equation, not over here, but actually, well, this differential equation is this one actually. So we are going to substitute ypt over here, and so okay, let me do this over here. So since my ypt is of the same form as my input signal, okay, so what we assumed is as a real number, some real number, capital Y e of 3t ut. Okay, I mean, either you can write ut, or if you're not writing ut, then it explicitly defines that the function is defined for t greater than 0, right? Now let's substitute this in the differential equation to find what is y. So the first term is the derivative of ypt, so that will become 3 times y e3t. Okay, and then you have plus 2yt 2y e3t. Okay, e3t ut is there, on the both on the left hand side and the right hand side of the equation, so let's not write this down over here. So that is, the right hand side is your xt, which is k e3t. Okay, now it's very easy to see what is k in terms of actually we're finding y, so this simply implies that 5y is k, right? 5y is k, or y is, in terms of k, is k by 5. So that is your forcing function, that is your particular solution, that's it. The particular solution ypt over here is okay, is k over 5 e3t ut. That's it. That is your particular solution to the first order differential equation. Okay, given the forcing function is exponential. If the forcing function is sinusoidal, then we would assume ypt as some other constant. Okay, for example, over here we assumed it to be some other constant y, but real. So we would assume some other constant, let's say b, c, or whatever it is, multiplied by cosine of omega t or sine of omega t, okay, of the same frequency. So if xt was, again, if xt was a sinusoidal, then my forcing function would be some constant multiplied by the same excitation, that is sinusoid, okay, of the same frequency. And then again we would have substituted this in the differential equation, and would have found out what this unknown constant is, okay, in terms of the input. Okay, all right, now so y is a number that we must determine, and we have done that. So substituting xt and ypt into the differential equation for t greater than 0, will yield y is equal to k by 5. So this is your ypt. So we have a particular solution with us. But to complete the solution, we must find the response of the system to zero input over here, right? So to do so, in order to determine the homogeneous solution or the natural response of the system, we have to size the solution of the form. So we assume that yst is of exponential nature. Okay, that's how classically you solve the differential equations. And if you might have come across the solution of differential equations in your earlier courses on ordinary differential equations, ODE, as well in electrical engineering programs. So this is just a revision or revisiting the solutions of homogeneous solution to homogeneous differential equations. So for homogeneous differential equations, you assume that the input is 0, and then you assume an exponential solution to this homogeneous uh, differential equation. Then substitute this in the homogeneous differential equation, just like for the particular solution. But here, over here, there is no excitation. So if you substitute AEST in the differential equation, the first term is the differential, and you will have this SAEST, and then simply add this up. You will find what this, you'll come out to find that S comes to minus 2 over here. Okay, so S is minus 2. Therefore, the homogeneous solution is capital AE minus 2t. Again, there is an unknown constant, but at this point in time, you should not be tempted to find what is capital A. Just leave it as it is, okay? Because first we have to complete the solution. The complete solution will consist of both parts, the homogeneous part and the particular part, okay? Now this is for any choice of A. We don't know what A is. So utilizing this fact and the particular solution in the original differential equation, we find a solution to the differential equation for t greater. So this is the complete solution, okay? Although there are unknown constants, okay? This A is the unknown constant. So, but it shouldn't be found out at this point in time, okay? After you have written the complete solution, then you have to invoke some supplementary or additional information regarding the system, the behavior of the system, to find these unknown constants, okay? Now, as noted earlier, the differential equation by itself does not specify uniquely yt to the input xt, right? So over here, now we have the relationship of yt in terms of xt. Well, yt is basically the output. That is showing that the output is again of the exponential nature. There are two exponentials, okay, which are linearly combined, and you know how the output is to the excitation that was an exponential right now, okay? But this is not explicitly being defined by this differential equation in the first place, okay? So this differential equation is not defining the input and output relationship. So this was the differential equation. So for the given input, we have found the output, okay, which consists of two parts, particular and the homogeneous. So in particular, the constant A in yt has not yet been determined. In order to find the value of A to be determined, we need to specify some auxiliary conditions. So different choices for this auxiliary conditions lead to different solutions and consequently different relationships between the input and output. So assuming the differential equation describes a causal LTS system, in which case the auxiliary condition takes the form of the initial condition at rest. That is for the causal LTS system. If xt is 0 for, let's say, t less than t0, then yt must be equal to 0 for t less than t0. That means that if there is no input, the output should be 0. That is implied by the linearity, right? I mean, if you're going to scale an input by, let's say, 2, the output is also scaled by the factor of 2. That is homogeneity, okay? And that comes in the linearity principles. And but if you're going to scale the input by 0, let's say, which means you're forcing a 0 input, then the output should be 0 as well. That is implied by linearity. So we are making a much simpler auxiliary condition to solve for the unknown constant A over here, basically. So what we are assuming is that that xt is 0, okay, for a certain time t less than t0, and we know the system is causal as well. We know the system is causal. It's both linear, it's causal, and time invariant. Then yt must also be 0 up until that time where the excitation is applied, where a non-zero excitation is applied. So from xt, we see that from example, xt is 0 for t less than 0, and thus the condition of initial rest implies that yt is also 0 for t less than 0. Okay, system is not going to anticipate when a non-zero input is being applied. That happens after t equal to 0. And after t equal to 0, there will be some sort of response, but the system doesn't know before the excitation is implied. Okay. All right, now let's substitute this condition. So evaluating yt at t equal to 0 and setting y0 at is equal to 0 yields. So over here, just you have to for t equal to 0, the y0 is 0. Okay, and you find A in terms of K, right? K is a constant associated with the input, right? K is here. So K was a part of the input, it's a constant. So you have everything, now everything is known. Okay, so y of t now completely defined is a complete solution of the differential equation, which consists of both the particular and homogeneous solutions with all the constant determined. Now, so this is where you require your auxiliary or supplemental additional information regarding the system, and we have invoked the principle of causality and initial rest conditions for linear systems, and we have just found out this constant. But you must remember that if you are going to change your initial condition, then this constant is going to change, and this constant is going to change, the solution is going to change. So different auxiliary conditions lead to different solutions, right? So again, it is important to emphasize the condition of initial rest does not specify a zero initial condition at a fixed point in time, but rather adjust this point in time so that the response is zero until the input becomes non-zero. So until there is no input, there is no output. Okay, so that is what is being implied here. So thus for xt equal to 0 for t less than t naught for causality a system, yt is 0, that system is at rest, and we would use the initial conditions yt 0, y at yt not equal to 0 to solve for the output, right? So now this was the first order differential equation. Then if you recall, the order was 1. Okay, first order, this was the first order differential equation. It just has a first differential to it. Now the same idea can be generalized to an nth order differential equation. Okay, so an nth order linear constant coefficient differential equation can be expressed by the general relationship. Now n is the highest differential of the output that's being shown by this difference equation. Similarly, m is the highest differential of the input, but it is n that defines the order of the differential equation. So the order refers to the highest derivative of the output appearing in the equation. So in case n equal to 0, okay, then that means zero other differential is this y of t, and you just have a naught over here, so you can bring the a naught to the right hand side of the equation, and then you're left with the differentials of the input. This equation means that in order to compute the output, you just need the differentials of the input, or probably you need some past or future past values of the input. You just need the inputs. You don't need the output, past outputs, to compute the present output, right? So in case yt, in this case yt becomes an explicit function of the input, right, and its derivatives. So it's only depending on xt and its derivatives. So for n greater than or equal to 1 specifies the output implicitly in terms of the input. Now, in the case of the analysis, the equation proceeds just as in our case of the first order differential equation. So that means yt is again going to consist of two parts. One is the particular solution, and then plus a homogeneous differential solution to the homogeneous differential. This is the homogeneous differential equation because the input over here is 0, right? The input is 0. So for the input being 0, you again assume the solution, the homogeneous solution yht. So you see over here, if you make the right hand side equal to 0, the input is 0. You're left with the left hand side, which is non-zero, consists of nth differentials of the output, and then you go on assuming that okay, yst is of the form again ast, okay, aest, again it's an exponential solution, and you solve this for the homogeneous, you substitute this homogeneous solution in the differential equation, okay, and solve this for s, right? And what are the roots of the differential equations? So the roots are going to give you the value of s again, okay. For example, if it is a repeated root, then we have to multiply this with the s, but the same number of times. So the solution to this equation are referred to as the natural response of the system, because the excitation again is 0, right? And then whatever is the nature of the forcing function, you have to add this yst to the y particular solution, and then you have the complete output y of t. Okay, so y of t is again going to consist of two parts, particular solution and a homogeneous solution to the homogeneous differential equation. So as in the first order case, the differential equation does not completely specify the output in terms of input. We need some additional information to determine the complete input-output relationship for the system. So once again, different choices for these auxiliary conditions result in different input-output relationships, right? Now, Let's apply the same analogy to the discrete time systems, which are defined by linear constant coefficient difference equation. So they are the counterpart of the differential equation. And similarly, an nth order linear constant coefficient difference equation describing a discrete time system consisting of nth order difference of the output is defined as such. Okay, so an equation of this time can be solved in a manner analogous to that for the differential equations. Specifically, the solution y of n can be written again as the sum of particular and the solution of homogeneous equations. So the same thing is being applied. So if you make the input as 0, then you're left with the homogeneous part of the difference equation, and again you assume that the response is of exponential nature. Okay, the response is of exponential nature. So it will be some constant, let's say k e of mn. Okay, so just substitute this, find what is m. Okay, and this will be your homogeneous solution. But to add to this, you have to add the particular solution, okay, to form the complete solution. The complete solution, again, y of n will be yh of n plus yp of n, and yp of n will be of the same form as the excitation. Okay, but once there is no input on the right hand side, that means the natural response. We are evaluating the natural response or the homogeneous response of the system. So as in the continuous time case, the difference equation does not completely specify the output in terms of the input. To do this, we must specify some additional conditions. While there are many possible choices leading to different input-output relationships, we'll focus on the most part on the condition of initial rest. That is, since we are talking about LTI and causal systems, that is x of n will be 0 for n less than n naught, then y of n will also be 0 for n less than n naught. And this is a consequence of linearity and causality, right? So with the initial rest, the system described is causal and LTI. So the difference equation can be rearranged in the form, okay, you can write it as such. So writing this as such, well, this clearly shows that in order to compute the present output, you need the past output. You need the past outputs, and you need the present input for k equal to 0 and the past inputs. If m is a positive quantity, right? If m is a positive quantity and n is a positive quantity, that means past outputs and past inputs together with the present input and scaled by some constants, right? Which is bk's and ak's over here. So y of n is directly expresses the output at time n in terms of the previous values of the input and the output. So from this, we can immediately see the need for auxiliary conditions. Why do we need additional conditions? Well, to find these unknown constants, we don't know how what are the values of these unknown constants, right? So again, in order to calculate y of n, we need to know the past outputs. So therefore, if we are given an input for a set of auxiliary conditions such as the previous inputs, the above equation can be solved for successive values of y of n, right? We'll take one example to understand what it says. So the above equation is called recursive. Well, the recursive is a term used in the language of signal systems to show that the output requires recursion, that is, the output requires the previous outputs. Okay, so in order to compute the present output, we require the previous outputs as well. So it specifies recursive procedure for determining the output in terms of the input and the previous outputs. Okay, if it doesn't require any previous outputs, then it is non-recursive. Okay, so y of n in the form of if this n is 0, I mean, if you don't see this part, okay, that is non-recursive. But this is recursive. This is recursive. So in the special case when n is 0, the difference equation reduces to. That means there is no recursion. Okay, it just needs the present input and the past inputs, only inputs, no outputs. Okay. So y of n is an explicit function of the present and previous values of the input. For this reason, the above equation is also called the non-recursive equation, since we don't not recursively use the previously computed values of the output to compute the present value of the output, right? So over here, we don't need any past outputs, therefore non-recursive. This is non-recursive, and therefore we do not need auxiliary conditions in order to determine y of n. Furthermore, the equation describes an LTI system, and by direct computation, the impulse response of the system is found by you just substitute for x as delta function, unit impulse function, the same weights. Okay, so this happens to be the impulse response of the system, and you see that this impulse response has a finite length, right? That this length is determined by the capital M. So such systems are also called FIR systems, which has finite impulse response, right? So finite impulse response are mostly they're recursive, but it doesn't mean they cannot be computed non-recursively. They can be, but For example, over here it looks like that even if, for example, if m is 1, okay, then y of n is basically 1 over a naught b naught xn plus another term, okay, this is in brackets, plus another term b1 xn minus 1. So that means there is no previous output that is required to compute the present output. Okay, there's no y of n over here, so this is non-recursive. But okay, FIR systems having finite impulse sequences or finite length of impulse sequences can also be computed recursively. This is non-recursive. How? You see, if you look at this output, well, I can also write this as y of n minus 1, y of n minus 1, and if let's normalize a naught, b naught, and b1 to 1. Okay, so y of n minus 1 will be x n minus 1 plus x n minus 2, right? X n minus 2. And if I try to relate the present output in terms of past output, then y of n, the difference of y of n minus y of n minus 1 will be what? This will be x of n, and this xn minus 1 and xn minus 1, they cancel, okay, and you're left with xn minus 2, right? So over here, this is the same system, but it requires the past output as well. So you see, there are many ways to describe the same system by different difference equations. So I mean, this difference equation is defining recursion. This difference equation requires recursion to compute the present output y of n. So now you have so it doesn't mean that finite impulse response systems are always recursive. They could be non-recursive as well. So the impulse response for it has a finite duration, that is non-zero, only over a finite time interval. That is what is implied by the term FIR. Because of this property, the system specified by h of n is often called as FIR system. So although we do not require auxiliary conditions for the case n equal to 0, such conditions are needed for the recursive cases. But I mean, it is saying recursive cases, but FIR system can also be non-recursive. Okay, they can be recursive, they can be non-recursive, right? So let's take an example. So consider a difference equation, right, and which can also be expressed as y of n equal to xn plus half yn minus 1. Okay, so we are just rewriting the term to show that the output requires a past output as well, so there is a recursion. So highlighting the fact that we need the previous value of the output to calculate the current value. Thus, to begin with the recursion, we need an initial condition. So for example, suppose that we impose the condition of the initial rest and consider them. So the input is a unit delta function, okay, unit impulse function. So in this case, xn is 0 for n less than equal to minus 1. The condition of the initial rest, that y of n is 0 for n less than equal to minus 1, so that we have an initial condition that y of minus 1 is 0. Okay, we are assuming initial rest condition. So starting from this initial condition, we can solve for successive values of y of n. For example, we start with y equal to 0, then x is 0, okay, then half y minus 1. So over here, so we are putting substituting for n 0, this is y0 is x0 plus half y minus 1, and y minus 1 is 0, okay, that implies simply k. This is actually k delta n. Then for n equal to 1, this is for n equal to 1, this is for n equal to 1, this is for n equal to 0, okay, and we then again, to compute the present output, you need the past output, and guess what, the past output y of 0 is k, so let's substitute k over here. What is x1? x1 is delta 1, that is 0, then that implies this is 1 over 2k. Okay, then again, to compute the output at the present time instant n equal to 2, you need the past output y1, and y1 is one half of k, right? So if you substitute this over here, then that means 1 half squared k. And if you continue this trend over here, then y of n is x of n plus half 1 over 2 yn minus 1, and the solution to that output is an exponential, is of exponential nature, that is 1 half n k. Okay, and that has to start with n greater than or equal to 0. So since the system specified and the condition of initial rest is LTI, its input-output behavior is completely characterized by its impulse response, right? Because the forcing function is itself is delta function. Of course, we are looking for an impulse response right now. So okay, if you set k equal to 1, then you see that the impulse response of the system, considering this example, is of such nature. It is half n u of n, and this is an infinite impulse response sequence. The length of the sequence is infinite, so we call this infinite impulse response. Okay, infinite length impulse response sequence. So note that the LTI system in 215 has an impulse response of infinite duration. In fact, if n is greater than or equal to 1, the difference equation is recursive. Right. So you see over here, this is already in a form of recursion that requires the fast output. So it is usually the case that LTI systems corresponding to this equation together with the condition of initial rest will have an impulse response of infinite duration. Such systems are commonly called infinite impulse response systems. Okay, that's all.